co-founder of Aqarios, a quantum computing startup and spin-off from the LMU, the University of Munich. Our okay. Our focus is on solving optimization problems and providing a cloud platform that simplifies the application of quantum computing to solve these optimization problems. Today's talk is going to be about the field of quantum computing, providing a realistic viewpoint on what quantum computing can do for us today, what it's going to bring to us in the future, and whether it's actually living up to the hype that we see all around the media. I know optimization is already quite a complex topic. Quantum optimization is even worse. So I'm not going to go into too much details today and just focusing more on the business perspective and what we can expect from the topic. So to start, let me just tell you a bit about us, about where we come from. So as I mentioned, we're a spin-off from the University of Munich, in particular from the QIR lab from the LMU, which was founded in the year 2016 and has therefore been working in the field of quantum computing for more than 7 years by now. The QR lab has always been working very closely together with the German industry, and it has also pretty quickly established itself worldwide. It was ranked among the top 12 quantum computing research institutions worldwide, among other major players such as Harvard, MIT, Oxford, and all the other big institutions out there. In particular, due to this very close collaboration with the German industry, there has been a certain point in time from which on the QR lab could basically no longer take on all the projects that they got. And in addition, some of the companies preferred to work with other companies instead of a university, also simply due to legal reasons and the possibilities. And the QR lab wanted to focus more on the research part as part of a university, obviously, whereas the companies wanted to go more into the practical applications of quantum computing. These factors and a few others then led to the decision to found a spin-off from which we then emerged, but not simply to do all the projects that the QR Lab can't do anymore, but instead to develop a scalable and automated solution that can help these companies, but also many more companies out there. An important selection of people can be seen here on the slide, which includes myself, but also our scientific foundation. I'm not going to go into too much detail here. They've been involved in some pretty impressive research in the field of quantum computing and AI, but you can find out a lot about them online if you're interested. And in addition, we currently, of course, it's not all of our team. Currently, we employ more than 30 handpicked quantum computing experts and software developers at Aqarios. But okay, let's get started with the topic that you might already have expected from the title of today's talk. Let's talk about the so-called quantum revolutions. So the journey of quantum mechanics basically started with the very definition of light, one of the most fundamental phenomena of our universe, whose nature has always kind of been puzzling scientists all around the world. Up to the 18th century, scientists widely believed that light simply was a particle. Just until the 19th century, where scientists conducted experiments that showed that, in fact, light is a wave, similar to how we know it from sound waves, for example. In the 20th century, scientists again were researching on light, and one more time, they proved that light is, in fact, quantized. It exists in discrete units, again, in particles, what we today know as photons. So basically, scientists found out that light has to be both a wave and a particle at the same time. And I know it makes this sound quite easy, but this was actually quite a big thing, quite a big breakthrough, something that people had never seen before, and actually it doesn't make too much sense when you think about it. And revisiting the so-called double slit experiment, which you can see in the upper right corner, details are not too important, showed that not only light, but also other quantum particles like electrons, or basically any other particles, exhibit this exact same behavior, which led to one of the fundamentals of quantum mechanics, which says that quantum entities like light, electrons, but any other particle as well, are both a wave and a particle at the same time. And to top it even more, they can basically switch between what they are depending on whether or not we're looking at them, which I know sounds weird, but quantum mechanics is actually pretty weird. These discoveries then set the ball rolling for even more fundamental discoveries about our quantum world, and also led to the development of technologies that we use all around the world today, such as, for example, lasers, which we use in surgery, in communication, or also for precise measuring, as well as transistors, which form the modern basis for basically all modern devices we're using, and atomic clocks, which we use in GPS or in precise timekeeping, as well as to study the nature of time itself. But that was only just the beginning, as by continuing our research in the quantum realm, we set foot into the so-called second quantum revolution, which is characterized by our ability to control quantum systems at small scale at will, and which is also the revolution we still find ourselves in today. This time it began in around the 1960s when a famous physicist called Bell proposed that quantum particles can become connected in a peculiar way that could not be explained with the laws of physics at that point in time. A phenomenon that became known as quantum entanglement, and which basically says that two or more quantum particles can become interconnected in a certain way, such that the state of one particle can instantaneously influence the states of the other particles, regardless of their distance, even if they're millions of light years apart, which is a property that's so counterintuitive that even Einstein, one of the arguably brightest minds of mankind, argued against it, calling it spooky action at a distance and contending that it was illogical and that we have to have a misunderstanding of this concept. Which, well, I guess makes sense. So Einstein just a few years ago proved in his theory of relativity that nothing can move faster than light. And now another scientist comes around the corner telling him about some instantaneous influence on arbitrary distances. But turns out Einstein was in fact wrong. Quantum entanglement is a real thing, though it does not break the laws of relativity. And just proving this in a more sophisticated and practical experiment has actually been awarded with the Nobel Prize in Physics just last year. However, actually, that's not the final chapter. Right now, we're gearing up for a third quantum revolution, one that centers on our ability to control large quantum systems, and which promises to bring game-changing technologies to us, which will disrupt many of our today's industries and fundamentally transform our everyday lives. What we're going to focus on today is how far away we are from this third quantum revolution, what it promises to bring to us, and of course, whether it's actually going to become a reality. But first, let's quickly switch topics and let's talk about one of the most significant challenges we're facing as humanity today, climate change. Even though it stems from various causes and it leads to probably even more problems, let's here just quickly focus on two key factors, health and energy. While these challenges that we see here are by no means trivial, for many we actually do have ideas and approaches on how we might be able to solve these. So the question is, how do we put these solutions into action? The answer for many of these questions is that we require exponentially more compute power than what we have available today. So the question basically becomes, where do we get this compute power? Well, we can first take a look at how we've usually done this, which is about improving our existing hardware by shrinking our components and fitting more components into a smaller area, which then allows us to do more computations in less time. This approach has one significant issue, which is closely tied to what is known as Moore's law. Moore's law tells us that the number of transistors in an integrated circuit roughly doubles every 2 years, which works for some time, but we're about to hit a major problem with this approach. Very soon, as we continue to shrinking our size of our transistors, we're about to hit a size regime which is governed by the laws of quantum mechanics, where in simple terms, our current technologies won't function as expected anymore. So what can we do? The best approach would be to instead embrace this enormous potential that the quantum world has to offer us and start building our technologies around it. When we talk about quantum technologies, there are three overarching fields where the capabilities of quantum mechanics can have a transformative impact. We talk about quantum sensing, which is about improving our existing sensors using quantum effects, leading to significantly greater precision. We have quantum communication, which provides a means of secure data transmission, in this case, even provable security. And we have quantum computing, which leverages certain aspects of quantum mechanics to introduce computational speedups and to potentially solve problems that are completely infeasible today. Today, we're just going to focus on the field of quantum computing. Here we have four archetypical use cases that we usually talk about. We have quantum simulation, which is about simulating complex quantum systems with applications in, for example, drug discovery or in material sciences. We have quantum cryptography, which is about providing ultra-secure encryption methods and potentially breaking our today's encryption techniques. We have quantum AI, where we improve certain aspects of our pipelines in AI and machine learning. And finally, we have quantum optimization, which is about solving optimization problems more efficiently and potentially addressing optimization problems that are completely infeasible today. So let's dive into one example. Here we take an example, a very prominent example from the field of quantum cryptography. But first, we have to understand the so-called RSA algorithm, which is an encryption algorithm that is used basically all around the world today to encrypt our messages and secure data transmission. So let's just look at a quick example to understand how this works. So let's say we are person A, and we are going to decide on two prime factors. Here we can simply use the numbers 3 and 7. When we multiply these prime factors, it yields the number 21. So what we do now is we're going to keep our prime factors 3 and 7 secret, and we're going to publicly release the number 21. Now let's say there is a person B who wants to send us a message through an insecure channel. What B does is B looks up our public number, 21, and uses this number together with an algorithm to encrypt their message, which then leads to a random string which nobody can read and which can be sent through an insecure channel without having to worry. Anybody can access the string, but of course nobody can read it, it's encrypted. Anybody can access our public number 21, but to decrypt the message, you need to know these prime factors that were initially used to make up the number 21. And since we've kept them secret, nobody can do anything, but when we receive the message, we can use the prime factors to decrypt it again. I've simplified the process slightly, but the general idea behind the algorithm is the same. So, of course, it's quite a trivial example. Anybody can guess that the number 21 is made up of the numbers 3 and 7. So any attacker in between that wants to intercept and wants to read the message can easily just guess the numbers. But what happens if we make the number significantly larger? This becomes an exceedingly challenging problem, in particular when we start dealing with numbers that have hundreds or even thousands of digits. So the interesting question here is, how long would our best known algorithm, even when executed on a supercomputer, take to calculate these prime factors in such large-scale scenarios? And well, to make it simple, the runtime explodes. The complexity increases exponentially. And to be precise, when we reach a size regime of around 2,000 digits, the runtime of our best known algorithm already takes longer than the age of our entire universe, which at 13.7 billion years is quite a long time to calculate two simple numbers, which is exactly why this algorithm is so secure and why it's so widely used. But yeah, you can already see a second curve here on the slide, which is one of the shining examples of where quantum computing holds incredible potential. Back in 1994, Peter Shor developed a quantum algorithm specifically for this problem, which uses certain aspects of quantum mechanics, in this case superposition and quantum entanglement. Details are not too important. And for this algorithm, even though the difference in the beginning is not too huge, actually where in the very beginning we even take longer using the quantum algorithm. But as the size of the number starts to increase, the disparity becomes huge, allowing us to solve even large-scale scenarios in a very reasonable amount of time. And in particular, also these scenarios that we use today in practice. So it's not an exaggeration to say that if we could run this algorithm and similar algorithms today, we could break basically any encryption method we're using today, which, no need to tell you, would lead to quite devastating consequences. But yeah, no need to worry, such a scenario hasn't occurred yet, and it's very unlikely to appear anytime in the very near future. So we've seen Shor's algorithm, we've seen the capabilities and applications of quantum computing. Now it's time for a reality check. If we have these amazing algorithms, why aren't we using them? And to address this question, we have to take a look at the actual hardware of a quantum computer. Here on the slide, you can see two images. On the left side is the ENIAC computer, the first general-purpose digital programmable computer, which was completed in 1945. This massive machine occupied an entire basement, measuring 15 times 9 meters and weighing more than 30 tons. It even required its own air conditioning system. However, by today's standards, this machine is probably outperformed by any cheap calculator you can find at a flea market in the village next door. On the right side, there is Google's Sycamore processor, a quantum computer that, like many other quantum computers, is still in an earlier phase of its development. It's also huge, it weighs a lot. Some of them require cryogenic cooling, since they're operating at temperatures near absolute zero. And all of them require very complex and complicated setups to preserve the very delicate quantum states. So similar to the early days of our classical computers, we can already run algorithms on these quantum computers, but the hardware is simply not sophisticated enough yet to run real-world and large-scale problems. To put this into perspective, let's look at some actual numbers. So let's again use Shor's algorithm as an example to break the RSA encryption scheme we've talked about before. In particular, let's talk about the 2048-bit RSA algorithm, which simply means that we use 2048 bits for our public number, which is roughly equivalent to 600 digits. This algorithm in this size is also widely used in practice today. So Fujitsu gave an estimation that we need around 10,000 qubits and 104 days to run this algorithm and to break the RSA encryption. Just a quick side note, a qubit is simply the equivalent in a quantum computer to a classical bit in a classical computer. And it's often used as a metric to measure the capability of a quantum computer. So let's also investigate IBM's quantum roadmap, as they are one of the leading developers in quantum hardware. They started their roadmap here in the year 2019, where they developed their first 27-qubit device. Up to today, their largest device has 433 qubits, and they have plans to release one with more than 1,000 qubits this year. In the year 25, they want to go more than 4,000 qubits, and in the years 26 and later, they want to provide between 10,000 and 100,000 qubit systems. So just looking at the numbers, one might actually think that we are quite close to running Shor's algorithm, right? So we need 10,000 qubits, and we're going to get them in the year 26 or maybe a bit later. So the question is, should we be worried? And well, I think you can already guess it, no, we shouldn't. And to understand why, we also have to take a look at a bit more of a deeper challenge that we face in quantum hardware. Our qubits are not perfect. In fact, they're far from being perfect, and there are three main issues that we're facing today. The first one are noise and imperfections. Basically, our qubits are very susceptible to noise from various sources, which leads to errors in our computations. And as our algorithms grow and become more sophisticated, this error grows. At some point, unfortunately, rendering any results that we get completely useless. Next, we have limited coherence times, which refers to the amount of time a qubit can maintain its quantum state, which is important for computations on a quantum computer, and which today can be quite short, ranging between milli to microseconds. And the final problem is scaling issues. So when we start adding more and more qubits to a system, the complexity of maintaining precise control and managing the qubit interactions increases exponentially. So quite some big problems. How can we address them? So the biggest problem that we have is this error that gets introduced during the computation. And for this, we can simply employ error correction, which today typically involves combining multiple physical qubits into one logical qubit. So we're going to do the same computation on multiple physical qubits to reduce the chance of an error happening overall when we afterwards take a look at all qubits and take the average or the majority, depending on what we want to compute. However, here's the catch. When we talk about qubits, we might be talking about different types of qubits. The 1,000 qubits we're going to get in IBM's device this year and the 10,000 we're going to get later on are physical qubits, which are noisy and error-prone. The 10,000 qubits we need according to Fujitsu's estimation are logical qubits, which ignore noise and error. So let's look at a fairer comparison. So Google estimates that we need around 20 million physical qubits and around 8 hours to run Shor's algorithm. From the point of view of the time, I think great improvement, not 104 days anymore, we're down to 8 hours. But from the point of view of the number of qubits, it's quite horrible. So we expect between 10,000 and 100,000 qubits, sometimes in the year 26 and later. But even at the higher end of this range, we still fall significantly short of these 20 million physical qubits that we would need according to Google. So the question that you might have is now, when can we expect a quantum computer that is actually capable of running this algorithm? And my answer to that is quite simple. I don't know. Nobody knows. And anybody telling you about a precise timeline is most probably lying. Well, we can expect the quality of our qubits to become significantly better in the coming years, probably not even requiring close to 20 million physical qubits at some point or a few years in the future anymore. There are simply too many unknown questions to give a very precise estimate for this algorithm. We don't know exactly how the number of qubits is going to increase. We don't know exactly how the quality is going to increase. Maybe we're going to find an even better error correction algorithm. There are too many aspects that we simply don't know. Okay, so now after kind of bashing the field of quantum computing a bit, let's talk a bit about why quantum computing is still important today. So many people would ask themselves, if I can't deal with quantum computers today, why should I already deal with it? Why can I come back in a few years or whenever they are ready? And I wouldn't blame people like that because a lot of people think like that. But actually thinking like that is quite a big mistake. You can't just go from a classical to a quantum computer from today to tomorrow. You need to build the knowledge, you need to prepare a team, you need to understand how this technology can help in your businesses. Compare it to when the first IBM System 360 came out in 1964, one of the largest milestones in the history of computer science, a machine that at that point provided unforeseen and incredible features. However, IBM announced this machine on the exact same day as they released it, so companies had no chance to prepare for it. Many companies were unable or very slow to take advantage of the system. But imagine what would have been possible if you had access to that machine years before. You could have prepared your team, you could have built processes to be ready to take full advantage of the system on the day it comes out. However, at that point, it simply wasn't possible. This time, however, things are different. We already have quantum computers, we have quantum algorithms. Everything is here and ready that you need to prepare yourself for the age of quantum computing. It's simply up to you to make the decision to take this opportunity and to invest into the future of yourself and your company. Or drawing a more recent parallel, consider the field of AI. AI has been steadily advancing for years or even decades. But it's only been this year that large language models became accessible to basically everybody, leading to a boom in AI that caught many companies off guard, being completely unprepared to smoothly integrate AI into their operations. As a result, we now see companies running around trying to find experts and somehow effective ways to integrate AI into their completely unprepared infrastructures. And unfortunately, I think we will see this exact same scenario with the field of quantum computing again. There will come a point in time from which on quantum computers will become able to solve real-world and large-scale practical problems. But just as they did with AI, I would bet that many companies will again see themselves completely unprepared to integrate this technology into their operations. A technology that is just as, or maybe even harder to integrate than AI is. So let's use this chance and revisit the initial questions that we had about the field of quantum computing and in particular the impending third quantum revolution. So the first question that we had was, how far away are we? Well, we don't know exactly. There are too many unknown factors. But to at least give you a rough estimate and not just leave you with I don't knows all the time, most experts expect that quantum computing will be able to provide practical value within this decade, so within the roughly next 6 years that are left. But at what end of this range it will be is again dependent on many factors, and in particular also the use cases that you're working on. So the second question was, what does quantum computing bring to us? And I think that's probably become quite obvious by now. So I want to quickly address one misconception here that many people have about this field. Quantum computers will not replace our classical computers. The technologies are fundamentally different. So even if we have a full-scale quantum computer ready today, this does not mean that, for example, all our current AI techniques or all our current optimization algorithms will become completely obsolete. They will go hand in hand with with the hardware and the algorithms that we're using today. So quantum computing is no magic. You don't need to be a wizard to be able to use it, but it won't also solve all the problems that we have today, and it won't replace all the technologies that we have today. But instead, they have many but specialized fields in which they will excel. However, in these fields, they will significantly outperform anything that we know today. So let's talk a bit about quantum computing in the near future. But before, I have to quickly tell you that my examples from before actually didn't reflect the whole reality. So Shor's algorithm is widely known not to be practically usable anytime soon. But again, quantum computing is not just about Shor's algorithm. The field of quantum cryptography is one of the fields that will require the most extensive compute power to be practically usable. But we still have the fields of quantum simulation, quantum AI, and quantum optimization, fields whose algorithms will require significantly fewer qubits to actually bring production value to us. And fields which will probably be one of the fields that will emerge significantly earlier. In addition, we also have another type of quantum hardware that I haven't mentioned at all so far, so-called quantum annealers, specialized devices that are specifically built to solve optimization problems, which are more advanced than hardware, and therefore might also be a candidate to bring us production value in quantum computing earlier than the other hardwares. And there is one very important approach to quantum computing I also haven't mentioned at all, so-called hybrid algorithms. These algorithms combine both quantum computers and classical computers, allocating the quantum computer to parts of the problem where it benefits most. For example, also only solving parts of the problem on the quantum computer, which might still outperform our current existing algorithms, but will not require such large devices to run pure quantum algorithms. So, as for the final slide about my general talk, about quantum computing, so before I tell you a bit about what we at Aqarios are doing, let's look at some further numbers. So here's an excerpt from a McKinsey study published in April this year. So what we can see here is that we expect by the year 2040, so a bit in the future, the market of quantum technologies to have a value of 106 billion US dollars, where the absolute majority comes from the field of quantum computing, up to 93 billion US dollars, but where we also have quite a wide range, starting from 9 to these 93 billion. So again, we see it's difficult to make precise estimations, in particular when looking almost 20 years into the future. But the probably more interesting number for you will be here at the bottom left corner, where we see the expected economic value generated through quantum computing, this time also a bit earlier, by the year 2035. So the expected economic value generated through quantum computing is expected to be between 600 billion and 1.27 trillion US dollars by the year 2035, where we, for this number, actually only consider 4 single industries: chemicals, finance, automotive, and life sciences. The industries where we expect the quantum advantage to emerge sooner than in other fields. So you can see the future of quantum computing can be quite exciting, and research is advancing rapidly, and new breakthroughs are emerging regularly. All right, let me tell you for the next few minutes a bit about what we at Aqarios are doing and how we are positioning ourselves in the quantum world. And to do that, let's quickly take a look at the current status quo in our quantum world, where we see a very opaque landscape of many complicated processes and infrastructures. So we very regularly see that companies have heard about quantum computing, but they don't know when and how and for what to use it in the first place. And even if they know this, the next question usually becomes what kind of quantum hardware and what kind of quantum algorithm is even appropriate for my problem. We have tons of different quantum hardware providers out there. We have tons of software frameworks. So even companies that have identified use cases often don't even know where to start. And looking at it from the point of view of the stakeholders, so we have a ton of different stakeholders out there who can benefit from the power of quantum computing, but most of them, again, lack the necessary knowledge, so they try to rely on, for example, consulting companies or on individual software developers or quantum experts who are either very difficult to find or simply not affordable for many companies out there. So what we want to do at Aqarios is we want to fundamentally work on changing this landscape. And we want to position ourselves as a central nervous system in this world, where we provide access to all of these different quantum hardware providers out there in a unified manner, in a unified framework. And we want to provide services for many different stakeholders out there without the need for them to know in detail how a quantum computer works, while still providing full customizability for those individuals out there who do know how to use quantum computing. And that's exactly what we're working on at Aqarios with our quantum cloud platform, Aqarios Luna, a platform that gives the business world the access to the quantum technologies they need in order to tackle the problems and challenges companies are facing when applying mathematical optimization. This means in particular, we want to answer these 3 questions from before for our customers. We want to show them when quantum computing should be used. We want to tell them which hardware and algorithm is appropriate. And we want to take the role of the affordable experts for them who know how to apply quantum approaches. So summarized in one sentence what we're exactly doing. We solve the most challenging optimization problems by intelligently applying the most suitable solution from all available quantum, hybrid, and even classical approaches. So to show this a bit more in detail, our platform is going to provide 4 services. The first of which is Luna Solve, and the service that we have started developing on first. The big picture here is that we want to allow users to solve their optimization problems with the best combination of software and hardware for their specific use case, which can be quantum, but which can also be a completely classical algorithm, such as, for example, I think the best well-known here would be Gurobi. We started developing the service first and have finished our MVP of the service last year, have since then, of course, continued developing it, but focused on building a scalable platform around it. Since we've gotten the first users onto the platform this year, and we plan to publicly release the first version of the service next year. Using the service, users can either bring in their own custom use case or choose from our library of pre-implemented optimization use cases, which currently should be more than 50 if I have the number correct in mind. Users can then access the platform using different entry points, either a graphical user interface. They can upload the problem in established industry modeling formats, LP files, MIP files, and so on. Or they can simply access our API or our SDK. In the next step, we're going to take the uploaded problem and transform it into a format that we can store internally for repeated application, but which can also be later translated into potentially the language of quantum computers. In the next step, we're going to, if desired, we're going to deploy our recommendation engine, which is a combination of AI, heuristics, and general domain knowledge that analyzes the use case instance and gives a recommendation on which hardware and which software or algorithm should be used to solve this problem in the most efficient way. If, of course, the user has the corresponding knowledge or wants for some other reason to decide on the algorithm themselves, they are free to do so. In the next step, we're going to take the problem and we're going to transform it into the language for the corresponding hardware. For the quantum hardware, this would be quite different from the classical algorithms. We're going to solve it on the hardware. We're going to take the output, apply several post-processing steps, and finally deliver the solution back to the user. All right, the second service is going to be Luna Bench, which is a benchmark framework that's provided to benchmark your use cases and algorithms against the state of the art in, again, quantum, hybrid, and classical environments. So this can be used to compare your algorithm to see if it's competitive with the state of the art that we have out there. Or you can investigate your use cases to discover a potential quantum advantage for this use case. Or in other words, whether quantum computing will provide a benefit over using classical computers. The service is still under development, but I quickly want to give a high-level look at how it's going to work. So we're starting the pipeline again with a use case, either from the library or a custom use case, and users can then next choose the corresponding solvers or algorithms that they want to use, such as here, for example, the Gurobi solver, but also, for example, the Quagga Plus solver, which is a hybrid algorithm that we've developed in-house at Aqarios. And users can choose the corresponding mathematical format for their use case and solver combination. In the next step, users can set the settings, either recommended or custom settings, anything that's relevant for the benchmark process. And afterwards, users can then choose the outcome that they want to get from the benchmarking process, raw results, metrics, comparison between solvers, or also some plots for visualization. So just a quick walkthrough of what this could look like. We could say we want to solve the traveling salesperson and the job shop scheduling problems using Gurobi and Quagga Plus, where we use Gurobi with a MIP format and we use the Quagga Plus together with a Cubo format. Then we're going to go simply with the recommended settings, and afterwards we want to receive the raw results and metrics and a comparison between both solvers, how often one solver was better, more efficient, faster than the other, and so on, which can directly be used either in an internal R&D department or also, if desired, for any decision making. Or another quick example, we could also say we have a custom use case. This time we want to benchmark a purely quantum algorithm, the QAOA algorithm. One time we're going to parameterize our QAOA using a QBO. One time we have our own quantum circuit. Next, we choose some custom settings and afterwards receive some comparison between the solvers, as well as some nice plots for visualization, which we can directly use in any report or in a scientific publication. Right, the next two services will be quick. So LunaQ is going to be our general access framework to quantum hardware, which unifies the access to these hardware providers such that users don't have to deal with each business model and with each framework and API and interface of all the different hardware vendors out there. We're also going to provide a wide library of algorithms and use cases, also outside of the field of optimization, in particular with another focus on quantum machine learning. So users can use this both being a quantum computing expert who simply wants to more easily develop and deploy quantum algorithms, and users can use this just to run and solve their use cases using quantum hardware. And the final service will be LunaLib, a library of best practice examples of using our platform, general knowledge in the field of optimization and quantum, as well as general examples and things that might be important for applying quantum computing. And it's more of a service for easy onboarding and discovering new knowledge. All right, that's it about our platform services, but actually that's not quite all that we're doing at Aqarios. So if you want to work with our platform, or if you already have a modeled use case, or you want to choose a use case from our platform, then you can simply use the platform services that I've just showed to you in detail. However, if you want to have your own use case modeled, if you want to learn something about a field of quantum technologies, we also offer the possibility to do individual projects where people can get a tailored project, a customized quantum solution, and very importantly, can learn something about the application of quantum computing for them and their team along the way. And of course, we offer the opportunity to integrate this directly into the platform services if someone wants to use this use case using the platform that I've shown before. Right, finishing the part about our services, let me quickly tell you a bit about the core values that we hold at Aqarios. So first of all, we are pragmatic, meaning we very much see ourselves as quantum computing company, and we do believe that quantum is coming, but we also know that it won't solve all of our problems today. And this is even true for a specific subspace such as optimization. Next, we see ourselves solution-driven, and we want to deliver these best solutions to our users and not force certain technologies onto them simply because they're being hyped. We're hardware agnostic. I think I've told it, I've said that a few times already. We're working with all of the quantum, hybrid, and fully classical algorithms, providing the best of all the worlds that are out there. And finally, we're transparent. This means we're not going to skew any results to get outcomes that fit a certain narrative, but we want to show the real performance and expectations of each algorithm at each time. Which, in combination, I would dare to say is something that you unfortunately very rarely see in the field of quantum computing. So, just a quick overview of some of the partners that we have at Aqarios. I'm not going to go into detail here. You can find out about all the projects here on our website if you're interested. What I want to talk about is that we try to focus on some of the bigger partners out there, some of the most important players in the areas that we're working in, which can also be seen here, our core verticals, logistics, energy, and the finance sector, such that we can find out about the actual pain points of these target customers in the verticals, and of course build our services and solutions in such a way that it can actually help these companies that are out there. And as I mentioned, non-exhaustive selection of projects and partners can be seen here on the slide. All right, wrapping up the part about Aqarios before I come to the summary of the talk, let's quickly talk about the journey that we've had so far and that we see for us in the future. So we've started in the year 21, where we started with projects, getting to know our first customers and building knowledge and the first software that we can then finally use to build our MVP, which we finished at the end of last year, to prepare for the first users that we got at the beginning of this year, before we then prepare for the public platform release, which will, as already mentioned, is scheduled to be next year. From then on, we want to focus even stronger on the development of the platform, as well as increasing our marketing, sales, and public visibility. As right now, we focus very much on building our technology, and we've been within our existing business network. But from that point on, we also want to become more publicly visible. To then prepare for building all of our platform services that I've shown to you before, for which we expect to have sophisticated versions ready by the year 2027, from which on we already want to have our platform as a standalone service with a global customer base, hopefully worldwide, to prepare for the next years where we attempt to capture the quantum optimization market leadership. All right, the final slide for today. Here I just quickly want to address one question that many of you might have had, and actually many of you might still have. Should you invest in the field of quantum computing? So I'm not here to convince you to run back to your superiors or even your CEOs to urge them to invest millions into the field of quantum computing by tomorrow. And if I were, you should be quite skeptical. I'm running a quantum computing company. I make my living by selling quantum computing products and services. But one thing I don't want to do is resort to fear-mongering and dishonesty. So if you're looking for immediate production-ready solutions for your problems that you have right now, quantum computing might not be the right fit for you, at least not yet. If, however, you're interested in investing into R&D and positioning yourself at the forefront of technological innovation, then quantum computing should definitely have a place in your strategy. So today it's not about providing immediate production value. It's about building your team. It's about preparing your processes and gaining an understanding of this emerging technology to be ready to benefit from it on the day it actually hits the market. When the right time to invest into the field of quantum computing is for you, unfortunately, depends on many different factors, which include your strategy, your goals, in particular also your use cases. Some use cases might be applicable sooner than others. Some companies might lose out on their biggest chance ever if they don't invest into quantum computing today. Others might not gain anything by building a quantum POC tomorrow. You need to look into your strategy of your company. You need to understand where quantum computing can help in your field to find out when the right point in time is for you to look into this emerging technology. However, there is one tiny bit of advice that I want to give to all of you. So regardless of your decision, regardless of whether you think about investing into quantum computing, whether it's going to be today, tomorrow, a year down the line, or even multiple years down the line, please do keep an eye out on this emerging field. Quantum is coming. Quantum will revolutionize our very definition of computing power. And quantum will, at some point in the future, influence your business as well. So please don't miss out on this opportunity. And thank you very much for your attention.
Thanks a lot, Michael. Very, very interesting and transparent presentation. Any questions from the audience?
Quantum mechanics is, by definition, a probabilistic theory. We are dealing here a lot of times with deterministic calculations. So that's one question. The other thing, you talked a lot about, obviously, the noisy situation. There is another aspect that I've picked up over and over again. It's the heavy overhead that is required from a data input and data output perspective that eats away a lot of those quantum advantages. So these two questions.
Mm-hmm. So for the first one, yes, you're absolutely right. Quantum mechanics is inherently probabilistic. That's the very nature of quantum mechanics itself. And that also plays a big part in quantum algorithms. So quantum algorithms are not deterministic, obviously. So you never get a 100% chance of getting the same result or getting the perfect result when you run any algorithm. But what quantum computing is all about is working with these probabilities. This is also one of the inherent powers of quantum computing, actually. And when you run an algorithm for a certain time, or when you run it using a certain number of operations, you can increase these probabilities to a percentage where basically you can say it's a deterministic algorithm. You're not going to get the answer 100%, but it's going to be 99.9999. You can basically say it's going to be deterministic. But yes, it has a probabilistic nature, that's true. For the second question, yeah, there is also, I think what you're probably referring to is in particular the encoding of a quantum algorithm on a quantum computer. This depends a bit on what kind of hardware you're using. In particular, D-Wave, one of the providers of the quantum annealing hardware, are having a big trouble with this approach, since encoding a quantum algorithm onto their hardware or finding a good encoding on the hardware is in itself already an NP-hard optimization problem, which is why they apply many heuristics to find a good implementation. But this is only very bad in the very beginning, as long as the quantum hardware is very limited. Once it grows, the encoding of the algorithms it's more easy to encode algorithms and problems onto the quantum hardware. It's still going to be a problem in the future, but also something that many companies are researching on right now. But yes, this is also one of the challenges we face in quantum computing, definitely.
Are there any findings related to the energy impact of quantum computing? Is it more energy saving or?
No. So at the moment, I wouldn't say that quantum computers are really energy or eco-friendly. So as I mentioned before, we have these huge systems that for many quantum computers have to cool them to temperatures near absolute zero. You can imagine what kind of energy this requires. But that's also something people are actively developing on. And of course, it's a topic that's also present in everybody's minds, but I don't have the exact numbers in mind, but it's not that horrible that it's actually going to become a big problem once we have large-scale quantum computers. And of course, something that people are working on to reduce this energy consumption that quantum computers have right now, or developing even other types of quantum hardware that don't have this problem. So basically, you can use any any quantum entity to build a quantum computer with. You don't have one technology. You can use atoms, you can use photons, you can use superconducting circuits. There are tons of different approaches. Some of them require more energy than the others, and we already do have approaches which are not that bad in terms of energy consumption.